Okay, welcome everyone. So let's wait for 5 more minutes to see if other people join. Then we can start at 6:05. Okay, so let's begin. So welcome everyone. Uh, let's start the session for today. So this is NOC24 W139 NPTEL tutorial session on microelectronics devices to circuits. The course instructor is Professor Sudev Das Gupta from IIT Roorkee. I am Debashish Nandi from IIT Kanpur. I am a PMRF scholar here. So, as you know that we are at the week 12 of this or the last session of this course. It will be followed by one additional session that will be kind of a summary session, which I will mainly touch upon the advanced memory thing as so far I have planned. So it will be on this Sunday, 3 to 5, our regular time. Okay. So yeah, let's begin. So it is asked that identify the following circuit topology. Okay. So how do we go about this? There are actually multiple ways to go about this. One way which is very straightforward. Let me discuss that first. So method one. So what we'll do, we'll just write the transfer function, try to find out the transfer function in this domain, Laplace domain. So what are the assumptions we'll make? The assumptions what we'll make is that ideal OPAMP, and secondly that as you can see that the OPAMP is in negative feedback. So what do you mean by ideal OPAMP? Your open loop gain is tending to zero, tending to infinity. Your input resistances at both terminals plus minus tending to infinity. Okay. So that is what is meant by an ideal op-amp. So under this condition, we know that we can use the condition of virtual short. Okay. Virtual short. So when virtual short can be assumed, so we know that our this node will be short. So from the diagram, writing your KCL at node A, will find what? We'll find your I1 plus I2 to be equal to I. Fine. So I1, I2 and I are marked. You can see that this is I1, this is I2 and I are marked. So I1 will be what? I1 will be V1 over R1 plus 1 over SC1. I2 will be V2 over R2 plus 1 over SC2. And I will be simply your minus V0 by RF. RF stands for the feedback path. Okay. So if we simplify this, what will we get? We'll get that this will be your SC C1 RF times V1 divided by 1 plus SC1 R1 plus SC2 RF divided by 1 plus SC2 R2 times V2 is equal to minus V0. Okay. So now you need to understand one thing, that when we talk about transfer functions, it is output over some particular input. Okay, particular input when other is nulled, others nulled. Okay, so suppose I want to find out the transfer function of V0 over V1, then it will be, I need to make V2 equal to 0. Fine. So now let me just add another page. Yeah. So if that is the case, now what we see that my V0 V0 is equal to your minus V1 times SC1 RF over 1 plus SC1 R1 minus V2 times SC2 RF over 1 plus SC2 R2. So what we can do to simply understand what kind of device, what kind of circuit this represents, is that make R1 R2 equal to 0. So what you are doing, you are basically shorting these two. Okay, as you can, because R1 and R2 are not mentioned, right? It is in series with your capacitances, so it will not affect. It may introduce a certain corner frequency by means of RC time constant, or it can change that. Apart from that, it is doing nothing else. Okay. So that part we will see in the next problem, that what makes this series or parallel combination of capacitances resistances, how it changes in the Bode magnitude plot. Okay, that will be interesting. So what we can see? We can see that now my V0 becomes minus V1 times SC1 RF minus V2 times SC2 RF. This is what why we are doing this, to get an intuition. Okay, so we can see that my V0, you remember that these are all are in the S domain. So V0 will be minus C1 RF, some constant, times S times V1 of S, minus C2 RF times S times of V2 of S. So now if I just keep it like this, so what you can see? Can you tell me what does this imply from your knowledge of signal systems and Laplace transformations? When you have a multiplication with the input, S as a multiplication term with the input, so that signifies the, in time domain, what? That signifies in time domain differentiation operation, right? Differentiation. Similarly, here also we have a differentiation. Fine. Okay. So if we have this kind of differentiation, and then on top of that we have this. This is a summation operation. So what kind of circuit this represents? This represents your a summing differentiator circuit. Okay, so this is the right answer. So that is the brutal way or the hard way to solve the problem. Now to get more intuition about this, what we'll do, we'll just break down this problem. We can see that, see, now if I just remove this, so we can simply look at this part, okay? So this is a summer, fine. That much you know that summing amplifier will give you this kind of topology. But there is a capacitance connected at the input with a feedback through via a resistance. Okay. So method 2, summing part can be easily observed from the circuit. Now what we will do, we will simply consider this. So what do you think the response should be? This is Vi, this is C, this is RF, this is your V out. Okay. So again, under the same assumption of ideal op-amp and the op-amp being connected in negative feedback, we can directly write that V1 over 1 over SC is equal to minus V0 by RF. So your V0 by Vi is nothing but minus SC RF. So what is this? This is called an ideal differentiator circuit or an active differentiator circuit. So how will the Bode plot look like? If you plot V0 by Vi in S domain, take magnitude, write it in dB, omega in log scale, then you will have a zero. Where is the zero? There is no pole, right? Or the pole is at infinity. The zero is at S equal to 0. So you will have a response something like this. Okay, fine. With a slope of 20 dB per decade. This slope. Now what will happen if you, let's say I just copy this circuit and instead of applying it here, I add a resistance and apply V in here. Okay. So what will happen now? So your Vi over R plus 1 over SC give me minus V0 by RF. So then your SCRF will give you what? 1 plus SCR, that will be equal to, minus of that will be equal to your V0 by Vi. Fine. Now if you take your V0 by Vi for this case, so you have a 0 at 0 and a pole at minus 1 over RC, right? So what will happen to this plot? This will stretch up like this, and then suddenly it hits a pole. So this will be the location of the pole. So this P will be equal to your minus 1 over RC. So you see how an ideal differentiator is turning into a high pass filter, okay, by just introduction of a series resistance. Okay, so what is happening basically in the frequency domain, it is introducing a pole at a location of P equal to minus 1 over RC. Fine. So you can see that this slope is 20 dB per decade, and as soon as you encounter a pole, your slope should reduce by minus 20 dB. So the effective slope will be 0 dB. Okay. So this is what is happening. So you see that this circuit is a differentiator, and this circuit having multiple input path makes it a summing differentiator. Okay. Okay. So you should understand how these high pass filters with active elements are being realized. Okay, because these are very important for your competitive exams or the entrance exams at master's level. Okay, so I think that's all. So let's move on to the next problem. So next problem asks us that at zero corner frequency, integrator behaves as what? Okay, so what is an integrator? Integrator is defined as your V out by V in should be in the form of some constant over S. Okay. And how will that look like? In the Bode magnitude plot, say this is your omega in log scale. This is your V out by Vi in dB scale. So what you have? Zeros, phi means no zeros, or let's say 0 is at infinity and pole is at 0. Fine, it has one pole. So pole means what? Beyond that pole you need to have a minus 20 dB slope, or at the pole location your output should be infinity, right? So how do you draw that? You draw it like this. Okay, the slope is minus 20 dB per decade. Fine. Now it is asked that at zero corner frequency, the integrator behaves at what? So if you want to realize the circuit, so the circuit with an active OPAMP will look like this. So you apply your input through a resistance, and you simply connect a capacitance in the feedback path. So this is your V out, this is your V in. So this will be your CF. Okay. So this kind of circuit will give you an ideal integrator kind of scenario. Fine. Now it is asked that what about the zero corner frequency? So how to achieve that? Let's say I introduce a resistance RF so that I can create a zero. Okay. So how to do that? Now if you write the transfer function, so you will have Vi over R, that will be minus V0 over 1 over. So what is this combination? What is the impedance of this? You have 1 over R equivalent is equal to 1 over RF plus SCF. So your R equivalent will be RF over 1 plus SCF RF. Okay, fine. So you will have what? So you will have V0 by R equivalent. So V0 by R equivalent. So basically R equivalent by R will be your V0 by Vi. So what is R equivalent? We have found out that it will be RF by R times 1 over 1 plus SCF RF. Minus of that will be your V0 by Vi. Okay. So now in the same plot, if I plot V0 by Vi, fine, then what will I have? At S equal to 0, I have a finite gain, that is minus RF by R. Modulus of that will give me something like this. It will not give me infinite gain. It will hit a pole at this location and it will give me, let's say this will be your location of your CFRF, the pole location. Okay. And this gain is your RF by R, and then it will give you a response similar to low pass filter. Okay. So we see that at zero corner frequency, our integrator behaves as a low pass filter. Another way to look at this is, let's say you have your S equal to 0. Then what will happen? At S equal to 0, capacitor will be open. So you are just having an inverting amplifier. So your V out by V in, by inspection, you can write simply, by inspection you can write minus RF by R. Fine. Now as S increases and tends to infinity, your V0 capacitor becomes short and your V out is connected to directly with the non-inverting, or with connectly directed to the inverting terminal or this minus terminal, or it will be connected directly through this. Okay, when S equal to infinity. So then my V out by V in will be 0. Okay, so that is what the response of a low pass filter is. Fine. At low frequency, it allows the signal to pass from input to output, and at high frequency, it blocks the signal. Okay. So that is how you intuitively and also by means of rigorous derivation, you can analyze the circuits. Fine. So let's move on. So in case of static design, question number 3, in case of static design, at every point of time, each output is either connected to VDD or VSS via, you need to fill in the blank. So let us take the easy example of a CMOS inverter. Okay. So what is the circuit diagram if you remember? So this is connected to your VSS, this is connected to your VDD, this is your V out, this is your gates are connected in this fashion, this is your V in. Fine. So when now let's assume that there is a load capacitance at this node. So when CL is charging, so what will happen? Let's say this is PMOS, this is NMOS. So PMOS on, NMOS off. So we can represent this as an on resistance, this as an open circuit, this is VSS, this is your on resistance, this is VDD, and this is connected to your CL. Fine. R on P. And let's say you have a R of N. So what do you think that the ratio of this R on P and R on off is? You can obviously note that R of N is much greater than your R on P, right? Similarly, when CL is discharging, then your PMOS is off and your NMOS is on. So reverse case will happen. So this will be VSS. So this will be CL, V0. This will be R on N. And there will be a very high resistance, almost like an open circuit, R of P. And this is VDD, let's say. So this path is this, this path is this. Okay. So you will have your, in this case, R on N much less than R of P. So you can see that the output or the load capacitance is connected to always through the least resistive path, okay, or the low resistive path. So you can conclude that output is either connected to VDD or VSS, or VSS is generally kept at ground for most of the designs. So you can this via low resistance path or low resistive path. Okay, so this will be your right answer. So it depends on whether you are in the charging cycle or in the discharging cycle of the load capacitance. So in each cases, the time constant will be determined by the on resistance of the PMOS for charging case or NMOS, right? You remember that we have calculated TPLH and TPHL. So TPLH means when my PMOS is conducting. So the time constant we found out via a first order RC circuit, it was 0.69 times R on of PMOS times CL. Okay, ignoring the internal capacitances of the MOSFET. Fine. So that is what it is. Moving on to the next problem. So for the circuit shown below, find the potential at node S. So we are asked to find out the potential at this node, this yellow highlighted node. Fine. So consider VDD equal to 5 volt. First, let us mark the voltages. So this is 5 volt, 5 volt, 5 volt. This is 5 volt. Fine. So now they want us to find out that what will be, and the threshold voltage of the device is given as zero point 0.6. Fine. So first thing you need to understand that to have a potential at node S, the transistors to have a potential at node S, all the transistors have to be at the on state. Okay, so that is the first requirement. Fine. So next what we will do, check the potential at node P. Okay, because this is my drain and this is my source. Similarly, this is my drain, this is my source. Drain, source, drain, source. Okay, so I need to check what is the potential difference between these two, which has to be greater than 0.6 volt. Fine. Okay, because then only my this channel will be formed or my drain or source should be connected, right? So what is the maximum value of P node that can be? Max value of P is 4.45 minus 0.6 or equal to 4.4 volt. Okay, it can be less than that also, right? But then what will be the issue? Suppose it is less than that. Let's say my P node value is somewhat 2 volt. Okay, so let's say P node gets value of 2 volt. Fine. Then this value, this will be, and suppose my Q node has some value greater than 3, greater than 2, let's say 3 volt. Then what will be the drain? Then the drain will, for let's say this is M1, M2, M3, M4. Then for the M2 transistor, my P node, which was supposed to be drain, will be acting like a source. Okay, so it does not help us to create the channel or for a current to flow from current to flow in a unidirection or from M1 to M2 to M3 to M4, that it prohibits. Okay, so that is not an option. So what the transistor will do, So it will, so by our logic, this is not an option, and my P node will assume the maximum potential that can be allowed to sustain the current flow or the transistors to be on. Okay. So now my P node has a value of 4.4 volt. Okay. And what about this drop? This zero point 0.6 volt is dropped across the channel or the channel resistance or the on resistance of the MOSFET M1. Okay. Now what about Q? What about node Q? Does node Q need to be at a lower potential than P node? It is not, right? It can sustain zero point 0.4 volt. Similarly, R can also sustain 4.4 volt and S can also sustain 4.4 volt. What is happening is that in every case, the channel is formed. Okay? And in every case, this difference is zero point 0.6 volt or the threshold voltage. Okay? So using this logic, QRS will remain at 4.4 volt. Potential at S will be fixed to 4.4 volt. Okay. So this is the series stack of transistors. So you might have a question that in which kind of scenarios this kind of structures are used. Okay. Let me give you an example. For higher power handling, RF switches are used in a stacked fashion. Okay. So let me briefly elaborate on that point. So what happens is that suppose this is your antenna. Okay. So how your devices are connected basically is like this. Let's say this is M1, M2, M3, M4. Okay. And this end you have the transmitter and this end you have the receiver. Okay. So when there is a signal at this point, you make this on and turn this one off. So and you turn this one off and keep this one on. Okay. for transmission phase. So your signal will come at this via this path, and if any reflux is coming from this receiver, so it will directly get grounded via this path. Okay. So once this reaches the antenna, then antenna will radiate. Okay. So this is how your mobile phones, in your cell phones or any, let's say, base station antennas or base transceiver stations, BTS locations. BTS locations are the locations where you see the cell phone towers. Okay. So these are the topology, basic topology of series. This is called series shunt topology of RF transmit receive switch. Okay. So now what happens that this guy may not, by the way, the receiving happens in the just the reverse fashion. Okay. In the receiving case, your M2 and M4 will be on and your M1 and M3 will be off. Okay. So that the receiving signal coming from this, let's say some signal, some signal is coming in this way, so then this will be off. So this swing will translate to this will be off, and this will be on, and this will be on. Okay. The receiving is happening in the same fashion. So what is happening? This yellow highlighted portion, you do not use generally single transistor. You use a stack of transistor, maybe 6 to 12. Okay. You connect it in this fashion, just the way we have shown in the last figure, so that your VDS does not increase. You know, right? Your ID VDS, if you see after certain point, it starts to break down. So it does not reach your breakdown voltage. Okay, or some higher order effects like impact ionization and such does not come into picture, or hot carrier effects does not degrade the performance of the device. That's why you distribute the overall power among a series stack, or we call it stack of transistors. Okay. Similarly, the same thing happens in the shunt branches also. So this guy is called, so this fellow is called shunt branches, and this fellow is called series branch. Okay. So, and this stuff is called stacking of transistors. So this is one of the examples where this kind of topology is used. Okay. So this thing you will encounter in, you will encounter this in your advanced RFIC design in your PG. Okay. There are other design considerations which I am skipping at this moment, because this course does not allow me to elaborate much on that. So, for example, breakdown voltages, on resistances, off capacitances, isolation, insertion loss, those kind of things you will learn in the higher order courses. Okay, when the time comes. So let's move on. So very similar kind of thing, but the connection is a little bit different. Okay. In this case, what is happening? The source of one transistor is connected to the gate of the next stage. Okay. So basically, Again, we are required to find out the potential at node S. So let's say this is 5, this is 5, this is 5, this is 5, this is 5. Fine. For the transistor to be on, for the transistor to be on, we know that P has to be 4.4 volt because we need at least a threshold voltage drop because my VGS has to be greater than VTH for NMOS, right? For on condition of the transistor. Similarly, I need a minimum drop of zero point 0.6 volt. Here also I need a minimum drop of zero point 0.6 volt. Here also a minimum drop of zero point 0.6 volt. So in this logic, if I apply simple calculation, so this is 0.4 volt, right? So obviously this Q node will be 0.6 volt lesser voltage. So that will be 3.8 volt. Then R will be at 3.2 volt and S will be at 2.6 volt. Okay. So you see the difference? To keep all the transistors on in this case, you need to, again the logic remains same. Your transistors need to be on so that there is a drop of at least the threshold voltage between your gate and source. In case of if it was a PMOS was given, then source and gate, source would be at the higher potential, at one threshold voltage higher potential than that of a gate. Okay, so this is pretty trivial. So let's move on to the next problem. So it is asked that find I0 in the following circuit. Consider the op-amp to be ideal. Okay, so considerations, ideal op-amp, right? Then negative feedback. So virtual short can be applied. So by the way, in last lecture or the last session, I have discussed how to check if your op-amp is in negative feedback or not. Okay. So given that, you also need to understand because why I am keeping repeating on this kind of stuff, that these are the considerations, these are the ideal op-amp negative feedback. This is very important because most of the undergraduate students do not understand that when to apply, when the virtual short concept can be applied. Okay, for example, if your device is in positive feedback, for just like in a Smith trigger, if you have read, so there will be oscillations. You cannot apply the virtual short condition just blindly. Okay, and also negative feedback does not always mean that your feedback is connected to the inverting terminal. This also I have explained in my last session, that it can be possible that even if your feedback is connected in the negative or the inverting terminal, the device can be in positive feedback. Okay, so be very cautious. So do always a sanity check. Okay, so this is ground from the virtual short concept. So now what is happening? One current is flowing in this path, one current is flowing in this path, another current is flowing in this path. So this is 1.2 divided by 6 or zero point 0.2 milliampere. So this is also zero point 0.2 milliampere, and the above branch will have 0.075
milliampere. So what is the current flowing in this? This current is 0.475 milliampere. Okay. So now if you apply KCL at this node, what is the input resistance looking into this? Input resistances are infinity, right? That means we can assume simply it as an open circuit. So all the current will flow through this path. Fine. Okay. So what is the current flowing through this path? Is 0.475 milliampere. Okay. So if that is the current being flown to that, what will be your V0? V0 will be nothing but 0.475 milliampere times 8 kilo ohm, and there will be a negative sign. Negative sign because this terminal is grounded. It is flowing from ground to a potential which should be at a lesser value. So it should have a negative sign. So this times 0.475 times 8 will give you minus 3.8 volt. Okay. So this is minus 3.8 volt. So what about the current flowing through this? This divided by 4. So that is 0.95 milliampere. Okay. So now we have a situation where I have a current flowing here is 0.475 milliampere. A current flowing in this is 0.95 milliampere, and you are asked to find out this current. So it will be simple, your KCL. So applying KCL at V0 node, I am also naming the node V0. Don't confuse that it is a voltage. How can you name it as V0? For your satisfaction, let's make it O. Okay. So what is the current? I0. I0 will be negative of 1 point. So this plus 0.475. So 1.425 milliampere. Okay. So it is very easy problem, but very easy to misplace the signs. Okay. So the purpose of this problem is to make you understand that virtual short is applied. You should understand that. And second thing, you do not get confused about the direction of the current flow. Okay. So you should be keeping in mind the sign of the current flow. Fine. Okay. So let's move on to the next problem. Okay. So a XOR gate. So how does an XOR gate looks like? So this is the symbol of an XOR gate. A B bar. So we are asked to find out the minimum number of, so note this, the minimum number of gates required, and we can only use two input NAND gates. Okay. So how to go about solving this problem? So just note the steps very carefully. Okay. So we have y equal to a bar b plus a b bar. Fine. Now what is your two input NAND gate, let's say M and N. So your F would be M N bar. So we need to look for this kind of expressions using basic knowledge of Boolean algebra. Okay, fine. So how to go about this? First thing you note that you have A bar B plus A B bar. You can write it as double bar because bar of A bar is A. Okay, because A bar bar, or let me write it in a general term, because F bar bar is equal to F. Fine. Now we use De Morgan's law. Okay, so A bar bar, so we have this outer thing, so we'll use decompose this part. Okay, this inner part will decompose. So how will we do that? We'll do A bar B bar dot A B bar bar. So we have used what? A plus B bar is equal to A bar dot B bar. So this is known also as, okay. Now what we'll do? We will again use De Morgan's law, and let me just write the other form. Okay. So we'll use what? A bar bar plus B bar times A bar plus B bar bar, and there is another bar or implicant. So now we have what? We have A plus B bar times A bar plus B. Fine. So you see the form of this F1, F2 bar. So we have found out our two input NAND gate. Fine. So we'll just keep making the circuit in parallel. So this will be our Y, that is A bar B plus A B bar. Now we have found out this. This is my F1, this is my F2. Now I need to realize F1 and F2. Okay. Now we need to realize F1 and F2 using two input NAND. So how can we do that? So we have F1 is equal to A plus B bar. Fine. So how can we write this? We can write this A plus B bar bar bar, right? Same strategy we have applied earlier also. Now we will use De Morgan's law. So by using De Morgan's law, how can I write this? This will be A bar times B bar, right? Similarly, F2 I can write B plus A bar, B plus A bar, 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 B bar, A bar. Fine. Now I use a trick. A bar B plus B B bar. And I just keep this. So what is this? This is nothing but your 0, because if this is B, this is universal set. If this is B, let's say this is B, so this will be B bar. So B bar means B intersection of B bar is nothing but phi or 0. Fine. So I can easily add that. When I do that, what can I have? I can take B common and have A bar plus B bar, and I can easily see that this is equal to B times A bar plus B bar is what? AB bar, right? Similarly, I can directly write this is A times AB bar bar. So now what I have? I have a 2-input NAND gate at this place, where one input is coming from your B, another input is coming from A, and this little guy is giving me this AB bar. So this is giving me, this is B, this is A, this is AB bar. So this is AB bar, this is B, this is AB bar, this is A. So F2 is nothing but your A times AB bar bar. F1 is nothing but your B times or B and AB bar bar. Okay. So how many gates we have? We require 1, 2, 3, and 4. Okay. So this is how you solve this kind of problems. So 4 gates are required to determine the to realize a 2-input XOR gate or exclusive OR gate using two input NAND gates. Minimum number required two input NAND gate is 4. Okay. So please solve this kind of circuits for all possible gates using 2 3 input 2 3 input NAND and NOR gates. Okay. NAND and NOR are called universal gates because any gate can be realized using NAND and NOR gate. I had given one home assignment regarding this 5 6 weeks back. Okay. I think you have done that. If you have done that, so following this would be very easy. How does computers solve this? There are sophisticated algorithms which finds sum of product or product of sum based on the choice of NAND or NOR implementation. One method I will name is Queen McCluskey. Okay. If you are a PG student, you should know this algorithm for your placements. Okay. Okay. So let me take a break for 5 minutes, then we can resume. Okay, so welcome back again. So this problem states that identify the logic implemented in the following circuit. So by the way, this case a few points to note. Common gate topology, pass transistor logic. Okay, so requires lesser number of transistors. Okay, so how does this happen? If this is A, this is B bar. So for an PMOS, this will be A times B bar. Why so? Because if you have a NMOS like this, right? And this is your this is A, this is B, and let's say this is Y. So this is A, B, and Y. So what will happen if both are 0? That means your transistor is off. Y will be 0. If 0, 1, let's say transistor B is 1, that means your transistor is on. So what will that lead to? A passing of the same, shorting the source and drain. Basically, the channel is formed. That means what? When the channel is formed, that means your Y will be equal to A, and that is 0. Similarly, when this is 1, this is 1, this will be 1, and when this is 1, this is 0, transistor is off, no channel, that means Y will be 0. So this is representing a logic A and B. Now in our case it is B bar. So obviously it will be A times B bar or A multi and B bar, right? Similarly this will be A bar and B, and when ultimately what is flowing? Currents are flowing, right? So Y will be simply addition of A B bar plus A bar B. What is this logic? This is nothing but your exclusive OR gate. What is the truth table of exclusive OR gate? 0 0 0 1 1 0 1 1. So when A and B both are 0, so that means Y will be 0. Similarly, when this is 1, it will be 0, and this is 1. Note that the name of exclusive OR comes from the fact that when any one of the input is 1, then only the output will be 1. When both are 1, both inputs, then it will not be 1, it will be 0. So this is exclusively OR gate, because in case of normal OR gate, this would be 1. Okay, so it is an XOR gate. Similarly, okay, let's go to the next problem. Consider the D latch shown in the figure, which is transparent when the clock input is high. Transparent means, what does transparent means? Transparent meaning is your Q equals to D. Okay, when the clock input is high and has a zero propagation delay. In the figure, the clock signal, clock 1 has a 50% duty cycle. What is duty cycle? duty cycle is defined as on time versus the total time, total period. Okay. So 50% duty cycle, and that is 1/3 period delayed version of clock 1. Okay. What is the duty cycle of this? 50%. What is the duty cycle of this? 50%. But you can see that if I draw a time scale, this is t equal to 0, this is t clock by 3, this is t clock by 2, this is t clock. Okay. So what is the time? So let us assume that it is level triggered. That means when your clock is 1, then only your Q will be equal to D clock, or CK, Q will be D or transparent. So what is that period? If I just mark that only this region, both clock and output is on, because we need to find out the duty cycle at the output. So we need to find out when my output will be 1. Okay. So for that to happen, first thing, my Q needs to be 1. That means my CLK 1 needs to be 1. And second thing, my clock needs to be 1. So both needs to be 1. So that is happening only in this duration. So what is this duration? So that is TCLK by 2 minus TCLK by 3. That will be 3 minus 2, 1 over 6 times TCLK. So what is duty cycle of output? On time is 1 over 6 times TCLK by period TCLK times 100%. That is 100 over 6%. That is your 16.67%. Okay. So that is what is happening, and how you determine the duty cycle of the D latch. Fine. Let's move on to the next problem. So DRAM, SRAMs are type of memory, and solid state storage is a type of dash memory. Okay. So for to understand this question, you need to understand the memory hierarchy. Okay. So what is memory hierarchy? So this is your processor. Okay. Now memory is divided into multiple levels. Memory is divided into multiple levels. So let's say this is your L1, then this is your L2, then this is your L3, then you have EDRAMs, then you have your DRAMs, or let's say main memory. This is conventional, okay? Today's scenario is a little bit different where we have additional storage class memories which I do not want to discuss today. That will be discussed in the next session or the summary session. So then you have your solid state memory, and then you have your hard disk drive. So can you tell me that what are these? These are called cache memories, okay? So these are basically made of your SRAM or static RAMs. This is your embedded DRAM. This block is your DRAM. So this portion, your static, okay? And these two are your dynamic. Dynamic means it needs refreshing. That means your DRAM will be something like this, okay? There is some capacitance. So these are your word lines and bit lines. So what happens is that your capacitance, suppose you are not refreshing your capacitance or the recharging your capacitance, so capacitance starts to leak, or the stored charge in the capacitance start to discharge or leak. So that reduces the efficiency of the storage capability of the memory. So this is your 1T1C DRAM structure, okay? And how about SRAM? SRAM will be something like this, your 60 SRAM. So this will be bit lines, this will be your word lines, okay? So you see that there are, this is your 60 SRAM structure, okay? Two transistors here, two transistors here, one here, one here. Charges are stored in these two nodes, or the memory are stored in these two nodes, okay? So this we will explain the detailed working of SRAM and DRAM in the next session. For today's session, just understand that above this red line, you have volatile, and beyond this red line, you have non-volatile type of memory. Volatile and non-volatile means when you plug off or switch off your device, the stored memory is erased. But in case of your power is off, then also when the memory is retained is called non-volatile. Okay. So by the way, in today's scenario, when you try to buy a laptop or PC, what do you see first? You see what is my RAM, right? What is that RAM we are talking about? That is the main memory of your computer, or this fellow, okay? That you call about 16 GB RAM, 32 GB RAM, right? In your mobile phones now you have 8 GB RAM, 12 GB RAM, 16 GB RAM, right? That is a random access memory That is what we are talking about is the DRAM. That is the main memory. That is also called the main memory. Okay. From main memory to the processing unit, where your arithmetic logic units are doing all the computation, there are data buses are running, okay, or the memory buses are running, or the lines are running. So you, whenever your instructions, you are giving one instruction to your processor, so that instruction is to be fetched from that memory. So that memory, that instructions, etc. are being stored in your main memory. Okay. What is cache? Cache is something which is shared by the processor itself. It is co-designed or co-placed in the same location at your processor. For example, if we talk about Intel's i9 processor, so your i9 processor will have a certain configuration of your cache. Your level 1 cache will be very close to your processor. It will be very lower value. You see the pyramid. So the dimension is such that as you go from top to the bottom of the pyramid, your capacity or the memory capacity increases. Or in other words, as you go down, capacity increases. But what happens? Your latency is also increases. Latency increasing means delay increases to fetch the instructions. So you want both, right? You want faster operation and higher memory. So that is why this multiple leveling or this hierarchy of memory was introduced or developed or evolved in the first place. Okay. So this cache memory is very much important to determine the processor speed. Okay. For example, your DRAMs are made by some different memory companies. For example, let's say your Micron makes some kind of DRAM, or SK Hynix make some kind of DRAMs. But these SRAMs are made by the processor companies. That is, Intel will make their design their own SRAMs. These memories come in a crossbar fashion, right? Row decoder, column decoder. This we will discuss in the next session. So it will come in a matrix form. So these designs are made by for SRAM by the processor companies itself. Intel does their own. Intel has their own SRAM team. AMD has their own SRAM team. Okay, but this DRAM and etc. are being procured from or purchased from other memory dedicated memory companies. Okay, so that is so far volatile memories. What about non-volatile memories? What about your SSD or solid state memory? That is the memory where your data is being stored in your laptops in today's scenario. Okay, earlier it was HDD, now it has been translated to SSD, solid state drives. Okay, for example, you might have heard that 1 TB storage in your laptop, that is your SSD. So even when you switch off your laptop, that is not erased, right? When you reboot your laptop, whatever the files, folders, videos, documents you have saved in your SSD does not get erased. Fine. And what about HDD? HDD is the external hard disk you use, the magnetic one. Okay. Hard disk drive. That is some kind of your flash or plug and play. Fine. So you understood the differences between the multiple layers and where everything falls into place. So from the question point of view, DRAM and SRAM are types of what? It is above the red line. So it is volatile memory, and solid state storage is a type of non-volatile memory. Okay. So the first option will be the right answer. Fine. So now let's move on. This will be the last question we will discuss today. As the number of participants were lesser, so we could finish the session much shorter in a much shorter time because of lesser interactions. So if your SRAM, yeah, You can
Yeah,
unmute and say, yeah.
sir, I have a sir doubt. We will discuss it after this question.
Okay, sure. So an SRAM has address lines. So general theory is that this I'll elaborate with crossbar design in the Sunday's class. So for now, you understood it in simply this fashion that something like this architectures. This is your row decoder and this is your column decoder or multiplexer. Okay. So and your memory elements are this. Okay. Let's say this will be your one memory element. So this is the structure, typical view. Details will be provided in the next session. So just to solve this kind of problem, how do you tackle this? Total memory size will be your 2 raised to number of address lines times your data lines. For example, let's say this is your address lines or address bits, then your decoder obviously will have a 2 raised to that value, right? If you have a three input, then your decoder will give you a 8 output, 2 raised to 3, 8, right? So similarly, in this case, we have 15 times this is data lines. In case there is a catch in this case, in the question it is mentioned about bits. Okay, so this 3 will lead to how much? 2 raised to 3. That means if this is, let's say these are the select lines and this is 3 input, so you will have what? 8 lines. So total you have how much? 2 raised to 15. This is bits times 8 bits, that is 2 raised to 15 bytes. 8 bit is 1 byte and 2 raised to 10, 2 raised to 5 into bytes. So 2 raised to 10 bytes is 2 raised to 5 kilobytes. This is your 1024, right? So 2 raised to 5 is 32 kilobyte. Okay. Note the capital B. Okay. So that is how you calculate the memory capacity of an SRAM array. I will explain in detail in next class how a 60 SRAM works. So please tune in for that. Aban, you had a question. Aban, you had a question. You can ask now.
Yes, sir, sure. Sir, I have two questions.
Yes.
First, sir, I haven't received the admit card yet.
I am not the right person to ask or answer about this. What you can do, you can directly mail to the NPTEL team, IIT Madras team, or you can raise a query in the discussion forum. Okay, that
Okay,
there the team will address that.
okay, sir. And I have a second question that, sir, like I haven't like studied till now. So
Okay,
yes, I haven't I have watched two three problem solving sessions, but I
okay.
haven't. Yes, so I have my exam on 26 also. Like, is it like how can you prepare in these 5 days or like in this coming days, sir?
What is
That
your
I was
background?
my MSc Electronics, sir. I just want to clear the this subject for credit transfer for my college.
No, no, that is fine, but what is your background? How much concept do you have? That will depend, that will take into account that how much, how much quickly you can cover. So what is your background on this? That you have seen the topics, right?
Yes, I have seen the topic. I have studied till second week,
So
and
are you comfortable among the topics? You need suggestion on preparing for the exam, or you do not have the basic understanding. Can you please clarify that?
yeah, I actually don't have the basic understanding. But when I saw the solution, solution of this, I was able to understand like how to solve and what if this type of question will ask, then how can I solve?
Okay, so what I'll suggest you that see it is a very tricky situation. So you have asked me that how to prepare for in within 5 days. So
Yes,
I'll suggest you that you first go through the assignment problems. Okay,
okay,
and pick any one of the TAs. Myself and Harsh Raj both are two TAs are there. You pick any one of them because our teaching styles may be somewhat different, so you may get confused between the two. So choose either my sessions or Harsh's sessions and
yes,
go through all the sessions in a fast forward mode, okay? So that you can get the methods quickly. And attempt all the assignments that has been assigned to you. So far 12 assignments have been given, right?
yes, yes, sir.
To solve those 12 assignments, if anywhere you feel that you are lacking the concept, so if you are in, let's say you are feeling that in noise margin you are having a problem, so you go to week 5 or week 6, you see that at which session the professor has posted the lectures. You just go through and watch those lectures. It will be much lesser time taking. So I think you can complete the if you do not have that much good basics, you should be able to complete it within 3 days, all the assignments. Then next 2 days you should revise, and then all the best for the exam.
Yes, sir. I was just asking, sir, if I solve all the assignment problem, is it
Okay.
like is it not enough? Because I saw the solution very like मतलब सही लग रहा था solution मतलब मेरे को समझ आ रहा था
No, no,
वो
that is fine, but you will not get exactly the same question in the exam, right? You will get
yes,
similar questions. So for to solve similar questions, you need to have a clear basics. So to develop that clear basics, so what I have suggested you, first you when the TAs are solving whichever the TA you are following, when they are solving the problems, you solve it along with a pen and paper, okay? Then try to attempt the assignment problems again at the later 2 days. That when they then you will not see the solution, you will just do it yourself. Then you will feel the confidence that you are not making the calculation mistakes, the basics are being captured correctly, okay? So you need to do the assignments twice, one with the aid of the solution provided by the TAs. Secondly, you have to do the assignments by yourselves, then you will be able to tackle the similar kind of problems.
okay,
Is
sir.
that fair enough?
Yes, sir.
Okay, so I think that's all for today. Let's end the session here.